Thank you very much. I fully agree with you that one of the problems that we have is high false positive in all areas of security. And really the art is to reduce it, because high false positive is as bad as low false negative. And I also very agree with you about the usage, the importance of usage of AI and machine learning. Okay, so I'm happy now to invite the last but not least, Avner Goren, who is VP of Architecture Graphic in Intel.
Thank you. Okay. It seems that we have lost quite of the audience. In any case, it's me, the only thing between you and actually going outside to the heat. So maybe you should stay. Let's just open it up. Okay, my name is Avner Goren. As just heard, my focus actually is SoC architectures, and my main focus area today is the areas of IoT. Not only, but IoT is one of the important ones. What I'm going to do, this is a cyber week, this is a cyber security conference, but I'm actually not going to talk about security, only until the last slide or so. What I want to talk about is AI. And eventually I'll close the loop and explain how does it actually all relate to security. And what I'm going to try to do is to tell you why AI is such a huge disruption to the whole market of IoT, and how is it going to impact the whole way we do things. And maybe one way to look at it is, first of all, understand that we are under attack. There is a flood of data heading our way. Just to illustrate, those numbers are for 2020, and we are talking about an average internet user generating 1.5 gigabytes of traffic a day. An autonomous vehicle generates about 4 terabytes a day. Not all of it goes up to the cloud, don't be confused, but the amount of data generated is unbelievable. A smart factory, we are here talking about petabytes. Now, we are not collecting this data just for the sake of collection. We are trying to do something with it. It's all about extracting some insights, either business insights or operational insights or security insights. Now, how well are we doing it today? Well, the results are pretty embarrassing. Take a look at the following. Of all the data, digital data, ever generated by humanity, if you look, actually more than 50% were generated in the last 2 years. I don't think this is a surprise. I think all of you would realize that. But the more amazing point is that only 2% of the data was ever used, meaning analyzed. So 98% are collected, but we do nothing about them. Why? Maybe I'll illustrate this with one example. If you go to one of those huge wind turbines, for example in the Goren Heights, they have about 1,000 sensors in the turbine. The operator sitting on the control panel looks typically at 3 to 5 of the sensors. All the rest are doing nothing. Nobody even looks at them. And the reason is because we as humans are limited. So the question is, what can we do about it? So for that, we have to look at alternatives, and this is artificial intelligence. So let's first of all put some sense in the different terms. So what is artificial intelligence? It's basically a program that can sense, reason, act, and the last point is the interesting one. It can adapt. For that, we need to have machine learning, which is the actual algorithm that performs that the performance of that algorithm is constantly improved based on looking at additional data. By the way, all of you are working that way. Your ability to make decisions is improving with experience, with being exposed to more data points or more use cases. But what I'm going to talk about is about deep learning. Deep learning is basically a subset. By the way, I'm encouraged. Everybody's taking pictures, so you're awake, which is good. Deep learning is basically a subset. This is a set of algorithms that can leverage multi-layered neural networks. And that's a big breakthrough. We have changed the way we do things, and let me explain that. This slide would try to illustrate that. So let's say that the task in hand is to identify a bicycle in a picture. We have used computer vision for quite a while. So we start by taking a picture and we try to improve the quality of the picture, remove noise, improve the light conditions, whatever. And then we actually deploy computer vision algorithms like identify age detection, for example. And then we apply rules. And the rules can be, for example, what is a bicycle? It has 2 wheels. Great. It has pedals. It has whatever. So we deploy some kind of rules that allow us to make a decision, is this a bicycle or not? AI doesn't work this way. And the reason is because we are trying to look for ways that we can constantly improve. What we have is that we implemented in hardware or in software, actually in both, basically a neural network. And what we are doing, we are running vast amounts of data. And this is labeled data against the neural network. Labeled data means those are pictures that basically say, is this a bicycle or is it not bicycle? And the neural network constantly trains on this data, and doing that, it changes the weights between the neurons. So eventually, it reaches some kind of a detection level that we are okay with. I don't know, 90-something% accuracy. And then we can actually take that model that was trained and move it to the end device, which is implementing what we call inference. It uses the same model and the same weights. And now when you have an incoming picture, it can detect, is it a bicycle or not? So the whole concept has changed. We don't need to define the rules. We need to provide labeled data. And the machine defines the rules by adjusting the weights of the neural network. How good is it? Well, it's better than humans. This is actual data, which shows what happened between 2010 to today. We're talking about 9 years. And this is detecting a human in a picture. Machines are today at 97%, which is better than humans, because we are talking about various light conditions, fog, whatever. Actually, machines are better. Even in speech recognition, machines are better than humans today. For a simple task like detect, play song, the accuracy is at 99%, which is better, definitely better than me, according to my wife at least. So, my point is that we have reached the level that machines are using machine learning and deep learning and are generating accuracy that is higher than humans. So if you look back at 2014 or 2015, this is what we call the early adaptation phase. What we did is simple tasks like recognize cat in a picture. What we used for that is basically either CPUs, meaning software running on CPUs, and in many cases we used actual GPUs, meaning graphical cards. We used simple programming concepts like C++ and some proprietary APIs. And what is interesting to understand, at that time, the workload worldwide of training and inference was roughly the same, because training is a very intensive task. If we look what's happened today, it's very different. It's different because today we are doing things like, for example, detecting a tumor in an X-ray. The complexity is by far more complicated. So we are in what is called the early majority phase. We are using CPUs, GPUs, but we have today dedicated hardware accelerators which are implementing neural networks in hardware rather than in software. Beyond that, we have been able to allow the data scientists to access this hardware by means of software layers that abstract the hardware, thereby making it much more easier, I would say, to deploy a new machine learning algorithm. So I'm part of Intel, so let me tell you in few words what we are doing. I recognized this trend, I would say, quite a few years ago, and have started deploying it in actually everything we do. So today we have solutions that implement basically deep learning on CPUs, on GPUs, and on accelerators. We do this both by adding instruction set, new instructions to all our CPUs, which are optimized for deep learning functions. We do this by dedicated hardware. For example, we announced that we have now, for a data center, for the cloud, an inference accelerator that is doing it all in hardware. Do notice that up there it says inference greater than training. Today it is reaching 10x, moving to 100x, and it will be 1000x. Why? Because there are going to be many more endpoints that need to do inference compared to training that would be typically done in the cloud. So my question is, what can we do today? And I'll use one example. Traditionally, we had surveillance cameras on highways, and they were basically able to identify a car. The next step was to be able to identify many cars in a densely, I would say, dense traffic. But today, what we are expecting machine learning to do, and we are doing that, is identify the car, identify the license plate, identify the car model, identify the driver, identify what the driver is doing, for example, using the phone. All this can be reached by a single video stream of the driver as he goes through the tollway or through the toll gate. And actually, we are able now to even identify who the driver is or how many passengers are there, meaning can he go to an HOV lane or not. So all this can be done in machine learning and deep learning today. So one might ask, okay, so where is this happening? Is it all in the cloud? And that's a common mistake. Training is typically done in the cloud. But in reality, most of the inference is done not only in the cloud. So the things are typically too lightweight to implement AI effectively. Those are microcontrollers, they are running from battery, they are running it's not the right place. But edge compute, which is on-prem server that is in, for example, in the toll booth, it would be right next to the toll gate, connected to all the cameras up there. There we can implement pretty significant horsepower, so we can do local AI. We can do it in the network itself, and definitely we can do it in the cloud. Why do we need to be able to do them all? There are three reasons for that. Number one, communication is not free. Actually, to transfer all this data up to the cloud in order to do the inference in the cloud is expensive. Two is actually latency, which is extremely important. Typically, working with the cloud, you can be anywhere in the vicinity of 100 milliseconds, which might be not fast enough. Not only that, there is no upper bound. It's statistical. And in many cases, you want to have some deterministic, for example, in industrial, you need deterministic access. And the last one is privacy. Not always do you want to go to the cloud. So we support all of them. Last one. So, where do we do this? Which IoT markets are going to be impacted? The answer is all of them. In my opinion, all the IoT markets are going to be impacted. So now let me close with the following question. Okay, how does it all relate to security? So there are many presentations that we have seen on how AI can be used for security. Clearly, you can use AI for better insights. But I would like to emphasize the reverse. How do we actually secure AI? And the reason I mentioned this is that it's not only protecting the code and protecting the data, which is what we do in anything else. It is really about the fact that it introduces new attack surfaces, which needs to be addressed. It starts by the fact that you could try to basically replicate a model that took you millions of dollars to implement just by multiple inquiries of inference that would allow you to reconstruct the model, avoiding the enormous development cost. And we need to protect against that. But even worse, we are at the age of fake news, where there is also fake data. And the question is, can you attack the inference and or the training with fake data? And the answer is definitely yes. So the question is, how do we protect against those new attack surfaces? And I think this is a challenge for the industry and for the academia. And with that, thank you very much.
Thank you. Thank you, Avner, for your interesting talk. And thank you all of you for attending.